Assalamu alaikum everyone. Today in this lecture we will learn about buck boost DC-DC converter. So in the buck boost DC-DC converter, within the same converter we have both step up and step down operation. The basic circuit diagram of the buck boost type of converter is shown here. So you can see the input voltage is V in here, and then we have a inductor, and then we have in the output side we have capacitor and the resistor. Now this switch can either be connected to position number 1 or it can be connected to position number 2. Now when the switch is connected to position number 1, then it basically energizes the inductor, and after a certain time when the switch is connected to position number 2, then the energy stored in the inductor is now basically the inductor is acting as the source, and then the output is fed from the inductor, and this is the basic operation of the buck boost type DC-DC converter. So when this switch is connected to position number 1, during that time, as it can be seen from the figure on the left, at that time the voltage across the inductor, so basically if I draw it here, so our VL, so this is our VL, this is our V in. So the voltage across the inductor is basically V in for the time from 0 to T on, or for the time when it is connected to position number 1. And when this switch is connected to position number 2, at that time our VL is basically V out. Okay, so using this volt sec balance equation, we know that the integration of VL, or the integration of voltage for the whole time period across the inductor voltage is equals to 0, and if we split it into two parts, that is from 0 to T on and from T on to T. So during the time from 0 to T on, this switch is connected to position number 1. So this is our position 1 and this is our position 2. So during 0 to T on, the switch is connected to position number 1, and during that time our VL is basically V in minus 0 dt plus during the time from T on to T, the switch is connected to position number 2 here, and at that time our VL is basically V out. So if we integrate V out from T on to T, then this is basically the volt sec balance equation. And if we do the integration here, that means we have now V in multiplied by T on plus V out comes from here, and then T minus T on, and after simple algebraic manipulation you end up with V out divided by V in, which is basically the gain of this converter, and then you get T on divided by T on minus T, and after some manipulation you end up with V out divided by V in is basically equals to minus D divided by 1 minus T. So now we can control basically the duty cycle or the on off time of the switch. So by controlling this duty cycle D, we can control the output and input voltage ratio. So when D is equals to 0, for example, at that time this D is 0, so our V output will be equal to 0. When D is, for example, equals to 0.4, at that time our V output is equals to minus 0.4 divided by 1 minus 0.4, which is equals to 0.6. And during that time, as you can see, that V out is basically less than V in, and this means that when your duty cycle is less than 0.5, during that time the buck boost converter is operating in the buck operation mode. Now if you increase your D more than 0.5, for example when it is 0.6, at that time your V output is equals to minus 0.6 divided by 1 minus 0.6, which is 0.4, and if you divide 0.6 with 0.4, then you basically step up your output voltage. So within the same converter you have both buck operation and boost operation. So the name buck boost comes from here, that this is the same converter that is used to either, by controlling the duty cycle D, you can use it either in the buck mode or in the boost mode. But one important thing here is that this is a inverted converter. That means the output voltage is inverted. We have a negative sign here. I will explain it in the next slide. Why this negatives is coming, from where it is coming, I will explain it. So basically this is the same converter that is used for both buck and boost operation. Now if your D is if D approaches to 1, at that time your denominator becomes approaches to 0. That means your output voltage approaches towards infinity. And when your D is basically 0.5, at that time your numerator becomes 0.5 and the denominator also becomes 0.5, and then it's if you have a negative sign here in the gain equation, that means it is an inverted operation, but neither it is stepping up nor it is stepping down. So for D value less than 0.5, it is operating as a buck converter, whereas for D value more than 0.5 and less than 1, it's operating in the boost operating mode. Now how the circuit is implemented in real life is you have a transistor here, a switch here, and then you place a diode in the backward direction, and you have the voltage source here. So this is our V in and this is our V out. Okay, so when this switch is on, so when this switch is on, at that time you basically energize the inductor. During that time the diode is reverse biased, so nothing flows here. So basically you are energizing the inductor during the time when this switch is on, and when this switch is off, at that time the inductor is acting as a source, and this inductor will feed the load. Now what happens here is that whenever your switch is on, that means during that time your current is flowing like this, and then it is energizing the inductor, and the polarity of the inductor voltage VL is like this. And as we know that the inductor current does not change instantaneously, so whenever you are turning off your switch, the inductor current continues to flow in the same direction as it was flowing before. So it will continue to flow in the same direction, and the polarity of the inductor voltage will change. So this is the inductor voltage polarity. The positive goes in the bottom side during the time when the switch is off. So for the time when the switch is on, the inductor is acting as a load, and when for the time when this switch is off, the inductor is acting as a source. Now when the inductor is acting as a source, that means when the switch is off, at that time the inductor current will basically flow like this, and then some part will go through the capacitor and some part will go through the resistor or across the load, and the diode will be forward biased, so the current will flow like this on the right hand side here. So when the switch is on, the inductor is energized, and when the switch is off, the inductor is acting like a source. And if we look at the inductor current wave shape, then the inductor current is, of course, this is we know that L di divided by dt is our inductor voltage. So this is our inductor voltage VL. That means if you want to get the inductor current, you have to integrate the inductor voltage. Now the inductor voltage, so if you consider the inductor voltage from the polarity like this, then you can see that for the time when the switch is on, at that time your inductor voltage is positive, but when the switch is off, the inductor voltage is basically V out, which is negative. So if we consider your V out, if you take plus sign here and negative sign here, because this is your ground point, so this is your ground point. So if you consider your negative from this terminal, so the current is entering from the bottom. That means the output voltage is basically negative. Okay, so the output voltage is basically negative, and if you integrate your VL, you get your inductor current like this. So it's going up for the time when it is charging, and then it's going down. The inductor current is going down when the energy stored in the inductor is dissipated during this time. And during the time when you have from 0 to t on, during the time from 0 to t on, your basically the inductor current is the same as the transistor current. So your transistor current, or the I in, so it's the same. So I in and IT, so this is your IT, which is basically the same as the inductor current during the on time. So during the on time, the inductor current, the current in the inductor is the same as the current that is flowing through the transistor. On the other hand, during the off time, the current in the diode is the same as the current that is flowing through the inductor here. So the current in the diode is like this. So it's the same as the inductor current in this part. And for the rest of the time, so the input current or the transistor current is basically 0 when from the time t on to t. That means during off time. So this is the t off time. So this is your t off time, and this is your t on time. So during t off, your transistor current is 0, while during t on, your diode current is 0. Okay, so the inductor current, the average inductor current can be derived from the area here. So this is our T on. So during the time T on multiplied by IL is basically the area for the whole time. So the average I in is T on multiplied by IL divided by T. In the same way, you can derive the average output current from the diode current equation. So this is our I diode, this is our ID. Okay, so the average output current is basically the time T off multiplied by IL divided by T. This is obvious because if you have if the T off decreases, that means if the duration of T off is reduced, that will reduce your I output. That means if this part is reduced, then your I out will go down. Okay, so this is your average I out, which is equals to T off multiplied by IL divided by T. Now if you you get the output I out, if you calculate I out divided by I in, you can basically write this like this: T off multiplied by IL from here. So as the average current you get from here, and the average input current and the average output current. From this ratio, you do the simple calculation, you end up with T off divided by T on, which is basically T minus T on divided by T on. You can express it like 1 minus D divided by D. Now, if you look carefully, then if you increase your D here, your output current I out is basically reduced. So for the time when your D value is less than 0.5, that means let's assume your D as when D is 0, that means I out divided by I in, this becomes infinity, that means this is very high. And when your D is, let's say, 0.2, at that time this is 0.2, so the denominator is higher than the numerator, so your output current is higher than the input current, and during this particular time the converter is operating as in the buck mode. And when your D is basically 0.5, that means that at that time your output current and the input current ratio is 1, that means the output is the same as the input current. And when your D is higher than 0.5, let's say it's 0.8, at that time your numerator becomes smaller than the denominator, so the ratio becomes less than 1, which means your output current is less than your input current, and during that time your during that time the converter is operating in the step up mode or in the boost operating condition. Okay, so the efficiency of the converter, of course we have studied that there are non-linearities present, non-idealities present in the circuit because of the stray resistances from the inductor, stray resistances from the capacitor, and of course the on forward voltage drop or the on resistance from the diodes and transistors. All this causes losses in the converter, and in this particular example we have only considered the inductor stray resistance represented by RL. So our efficiency is the output power, which is V out I out divided by our input power V in I in, and the output power is I square R, I out to square R naught, and the input power is basically the output power plus the loss. So this is the loss, and we are only considering the stray resistances from the inductor. And if you divide everything by I naught square R naught, then you end up with 1 divided by 1 plus IL divided by I naught square. And alpha is the ratio of the stray resistance with respect to the load R out. And then if you do this average output current relationship with the inductor current, average inductor current, then you can replace it with 1 divided by 1 minus D, and by doing some manipulation you end up with 1 minus D whole square divided by 1 minus D whole square plus alpha. And the gain equation V out divided by V in is basically your efficiency multiplied by I in divided by I naught, and your efficiency you just calculated it from here, so your efficiency comes from here, and then it's multiplied by D divided by 1 minus D, which is the relationship between your input current and the output current that you derived earlier here. Okay, so from that particular relation you have the gain in the form of duty cycle, which it can be written as D multiplied by 1 minus D divided by 1 minus D whole square plus alpha. Now if you plot these things as a function of D, that means as a function of duty cycle, if you plot this as a function of duty cycle. You can of course do that in your MATLAB. You can plot the efficiency and the gain as a function of duty cycle. Then you can then you will see that that your efficiency basically after some time the efficiency drops down. This is clear from here that as d approaches 1, so this is your 1 value, so as the d approaches 1, that means the numerator becomes 0. So when your d is 1, the efficiency is basically 0%, and when the d is 0, at that time the efficiency is basically high, and after some time you have a decay in your efficiency. And the gain equation, that means V out divided by V in, if you plot it, then you have a d here. That means when d is equals to 1, at that time this term it becomes 0. That means when d is equals to 1, it becomes 0. But due to this d, it has a character like this. So it has a peak value here, and then for the time when the duty cycle d is 1, the gain becomes 0. And we want to we try to operate or design this converter in such a way that you operate it with a higher efficiency point. So you can actually draw these things, plot it in a very simple. You can in MATLAB you can write a very simple script. You can take the value of d from, let's say, 1 to 100%. That means from you can take it from 0 to 1 actually, with a spacing of maybe 0.1, so it can be 0, 0.1, 0.2 like this, and then you can write a script which will give you this V out by V in. And if you know, of course, the alpha value, you can consider the alpha value. You can assume the alpha value to be in the range of maybe 1 divided by 1000 like this, and you can plot the efficiency and the gain to have a much clearer idea, like when particular time you have a at which particular time you have basically a higher efficiency, and you want to operate your converter at that efficiency point. There is a mistake. There is a d here, so it should start from here. It should start from 0. So it should start from 0, because when d is 0, at that time your gain is 0. So it should start from 0 obviously here. Okay, so what should be the size of the inductor when you design your buck boost converter? So what should be the size of the inductor? So the procedure is the same. We need to get the boundary condition. We need to get the boundary when our IL mean, or the inductor current minimum, is 0. So basically at the boundary, so as this slope depends on V in divided by L, and the falling slope depends on V out divided by L, and as you basically lowers down your L, that means the slope increases. So the slope increases, and there is a moment at that time when this inductor current barely touches the x-axis, and it goes again. So again there is an error here, so it goes like this, and then it falls back again. So this is the time when your inductor is operating at the edge of the continuous conduction mode, and we need to calculate the value of L for that particular condition. And to do so, basically the IL max, or the maximum of the inductor current, that can be written as IL plus half of the V out divided by L, 1 minus T multiplied by V. So multiplied by T. So this is the same formulation that we have used in the previous types of the converters. So the first the IL, and then half of the V out divided by L. So you can see it from here. we can see it from here. So this is our IL. So IL plus, as this is in the midpoint of this peak to peak value, so this is the midpoint of this peak to peak value, and the peak to peak value is basically, if you know the slope and if you know the time, so you know the slope here is minus V out divided by L. So V out divided by L is the slope, and the time here is T off. Now T off can be written as T off, can write T off as 1 minus D multiplied by D. So this is the time, this is the portion corresponding to T off, and this is the portion corresponding to the slope, and this is the half of it plus IL, or the average inductor current. This is equals to your IL max point. So this is your IL max point. So this corresponds to this point, and your IL minimum point is basically, you have a minus sign here. So you have a minus half of P out divided by L, 1 minus D multiplied by T. And at the boundary, your IL mean is basically is equals to 0. So you have one equation, and for buck boost converter, we know that our I out, average output current, I out is IL multiplied by 1 minus D. So you have your IL coming from here, so you can replace this IL in this part. So you have I out divided by 1 minus D is equals to half of this, and replace I out with V out divided by R, and from there you get the equation for your L mean, which is the minimum inductor value for continuous conduction. For choosing of our C value, so then our next task is to choose what should be the value of the capacitor for a certain ripple condition. So this is our inductor current. So this is the current that is flowing through here. So this is our inductor current. So this is the inductor current, and this is the diode current. So inductor current during the falling edge time is the same as the diode current, or ID, and this fixed value is our output current. So this is resistance, this is the resistor here. So when the inductor is discharging, the current is flowing like this. Okay, so this is your I out, the output current, which is across the resistance is fixed value, and the higher frequency part basically flows through the capacitor. So if you subtract this, if you subtract I out from ID, then you get your IC. The capacitor current is basically ID minus your resistive current here. So if you subtract it here, so minus I naught, this is minus I naught here, and then this is just the subtraction. So again, this particular time, this is the amount of charge that is stored in the capacitor in one phase. So this becomes dq is equals to CdV, which is equals to I naught. The value here is equals to I naught. So this is I naught multiplied by dt. So dt is basically the on time. So this is the on time. So on time multiplied by I naught. So this is the area, which is equals to CdV. So your CdV is I naught dt. I naught can be written as V out divided by R, and from here you can get dV by V naught, or the ripple factor here is d divided by CRF. You replace t, or the time period, with the frequency, or the switching frequency here. So depending on the switching frequency, depending on a certain switching frequency, you have to choose your capacitor in such a way that you meet your voltage ripple condition here. Okay. So now comes a numerical problem for buck boost type of converter. So in this particular numerical problem, it is asked that an inverting buck boost converter is operating at a frequency of 125 kilohertz, has a 50 volt low ripple DC input and has an output of minus 50 volt into a resistive load of 25 ohm. The inductor has a peak current of 8 amp. This implies that the converter is in the boundary of continuous and discontinuous operation. The output voltage ripple is negligible, and you are asked to draw the circuit diagram and label the important voltage and currents, and second you are asked to sketch the inductor voltage and current waveforms, and you are asked to calculate the value of the inductor, and in the third part you are asked to determine the RMS value of the transistors and the diode currents. So the first part is drawing the circuit and labeling it. So you have to, if it comes in the exam like this, then you have to label all the important voltage and current values. So what is your IT, what is your ID, like this. And then the second part says that they sketch the inductor voltage and the current waveform, what is the value of the inductor, and from the first part you can calculate the value of D, because in all the numerical examples the value of the D is actually comes from your output and input voltage. So from the gain equation, from the output voltage and the input voltage, you first calculate the value of the duty cycle D here, and you calculate your time period T from the switching frequency. So these are the first steps. So depending on the duty cycle and the time period, you know when is your T on and how long is your T off time. And to calculate the value of the inductor, you need to know you basically solve it by using L di dt equation. So VL is equals to L di by dt. So you know what is the VL. You can consider it for the on time, or you can consider it for the off time. So whichever time condition, on or off time condition you are taking, you have to calculate, you have to consider that particular time. So here we are considering the on time here. So this is our 50 volt during the on time. The inductor voltage is 50 volt, or is the same as the input voltage, multiplied by the on duration, which is 4 microsecond, because our duty cycle is 0.5 and the time period is 8 microsecond, and then equals to L, and di is 8 amp. This comes from the question. It says that the inductor has a peak current of 8 ampere, and when it is operating in the boundary of continuous and discontinuous operation, at that time your di value, or this is the peak to peak value, becomes 8 amp. So you can calculate your L value from here, and in part number C you are asked to calculate the RMS and the average value of the IT and ID. Now to do so, you need to first draw your IL value here. So this is 8 amp, and this is 0 because this is continuous and discontinuous operation. So your transistor current will be of course 8 amp here. You know this is 0 and this is 4 microsecond. So then basically you have to calculate the RMS and the average value of this transistor current, and then to get your diode current from here. So this is your 8 amp point, and this is your 0. Y-axis value is 0 here, and x-axis value is 8 microsecond, and this is 4 microsecond. Then you have to calculate your RMS and average value from this particular waveshape. Now in the exam, of course, it can be a little bit complicated than here. I may give you the value of the stray resistance, value of the inductor. I may give you the value of the value of the stray resistances here from the capacitor, or I can give you the on resistance of the diodes, or the loss from the transistor. I can give the efficiency of the transistor, or I can simply give you a data sheet of a transistor or a diode and ask you similar questions. But of course, in that case, you need to follow the data sheet to find out what what is the value of the efficiency, what is the amount of losses in the circuit, and how you can improve the efficiency. So the exam questions will not, of course, be as straightforward as the examples I'm showing here. It will not be as straightforward as it is. It will be a little bit complicated than that. Okay, so that is the end of our lecture for buck boost converter, and in the next class we will start Chuck converter, inshallah. So that's it. Thank you very much for your patience. I would like to close the recording now.